Welcome everyone. So this is the experimental part of the previous video's calculations, where I showed you how to get to the best possible solution for stacking Peltier units. And in this part of the video I will do the experimental part. So as you can see, I have my let's call it test bench. So hopefully you can see here is the water cooling radiator with two 12 centimeters fan, and the fans are blowing the air into the radiator. So this is a so-called push configuration. Both of them are pushing the air into the radiator, and there is no other things on the other side. So there are no fans installed there. And here you can see the water tank. I have this drain valve here with these three-way T-pipe and some valve here. This is the thermometer, which is attached to this block here, which also has a small kind of fan inside there, or some kind of propeller. So this is a flow indicator. This will be the cooling unit, so this will carry away the heat from the hot side of the Peltier units. And then regarding the experiment, I showed you something previously where I had this heatsink. So I first want to show you how to stack these Peltier units. So what we have is we have the cooling block, and then we have two of the selected Peltier units. Now these doesn't matter which I choose here. I just found these old units in my drawer, and these are good because they are slightly damaged, so I can do the demonstration on them. So we pick this unit, which is the water cooler, so this part here, and then of course we will apply some thermal grease. So now we imagine that we applied the nice even layer of and thin layer of thermal grease, and then we see that okay, this is the hot side, so that should come on this side of the unit, and you see that both of them are 4 by 4 centimeters, so they overlap perfectly, so you can see. And then of course we apply the thermal grease on this side, but that's not so good idea at this moment, because we want to be able to handle this without making our hands filthy. So what I would recommend to you is you take this and apply the thermal grease on the hot side of this, which will touch the cold side of the bottom unit. So then you can like hold this properly, or you can even like clamp it with your fingers while working with it. But the thermal grease actually between these two layers, so the hot side and the cooling block, will provide enough adhesion just so you can move around with it. But if you touch this and apply a bit higher force, then this will like twist and turn and whatever. So but for like handle it like this, it will be sufficient. So we have this unit, and then we have this unit. Imagine that we have the thermal grease on this side, so you put together, and what I suggest you now, you a little bit twist it, both of the units, just to spread the thermal grease. And of course you have to apply a little bit of pressure, so you can push out the excess thermal grease that you applied on the surfaces. So then you have this, and I suggest you to hold it like this by one of the edges. Maybe this is more comfortable, like this way, because these two pipe fittings can like hold your thumb or your finger. So yeah, it will stay there. And then either you put the thermal grease on the top side of your, so the cold side of your top Peltier, or you put it on the heatsink or whatever you use. I use this heatsink because I use this to clamp it. So you can see that there is a notch here. So I put this on it, and then I just grab it like this. So this will be a stable contact between the two units, so the heatsink and the rest. And now what I do, I have this aluminum block. So this is the 20 by 20 profile. So this is the extruded profile, and then I will put it here like this, and then I flip it. So this is now attached, And I have this, so you can see that this is a screw which perfectly fits into this rail here. And what you can also see, I applied some washers just to make up make up the difference between the length of the screw and the distance between this part and this part, because of course if you screw this too much, I will try to show, then the screw comes out and the screw will start to push against this profile, and you don't want that, because then you cannot pull the heatsink against the bottom part. So what I do, I slightly unscrew the screw, so the thread is still inside this nut, and then I put it here. And you can also see that there is a plastic sleeve here, so technically there is no thermal contact between the heatsink and the profile, or which is in contact with the hot side. So now this is in, and then I just tightly or slightly screw it in, but you have to make sure that that thing rotates in to that notch or channel inside the profile. And that is not an easy task, but it's doable. Even I could do that while explaining this thing. So now it's, and you have to make sure that this contact is not strong contact. You just first screw it in, so your screw will not move here and there. And you still apply some pressure with your finger. You make sure that these holes are aligned, and then you have your next part. And then we try to put it in, hopefully. So this has to be screwed down. I try to do that. So this black part has to go all the way up. I haven't checked this, so sorry for this mistake. So now it's pushing the washers, and this is fine. So this is still one piece. And now this is in. And now you can see that this is aligned perfectly with the channel. So I don't know if it's visible, but... And now comes the tricky part. You increase the pressure by the screws by tightening it just tightly, slightly tightening it. Sorry, I always mix up these words. So you apply like a very small turn, but if you feel resistance, just stop, because what you have to do here is you want to align everything parallel. And if you, let's say, apply more pressure on this side, then the heatsink will be tilted. And that's not only a problem because of the heat transfer between the different layers, but it's also a problem that you can crack or even break off the corners of these very delicate ceramic plates. And if you were cautious or careful when I showed these units, one of the unit already had a crack. So yeah, I don't know where or when, but I already did it. So you see, okay, you cannot feel the same force that I'm applying, but this is like showing a really good resistance now. So this is tightly screwed, and I can see that if I look into the channel, then the screw is not going through the nut and it's not touching the bottom of this channel here, and that's very good for us. And the same should go here. So I can see, I hope you can see, or something like that. So the screw doesn't go through the nut entirely, so it will not touch the channel. And because when it starts to touch the channel, the contact will be not the best. And now here I also see that, okay, this is like perfect, perfect resistance. And yeah, this will be enough for us, I think. And possibly you should be able to see some of the thermal grease coming out from the layers, because you like clamp it really tightly. So this will be the setup. So we will know that, okay, one set of cable will go to one power supply, which will provide more power for the stronger unit. And there will be another set of cables, and that will go to another weaker power supply, because we will apply lower power to that top unit. So this is just the demonstration how to put this system together. So what I will do, I will use this block and recreate this setup, but now with my proper units. So I will use the TEC 12715 in the bottom part, so that will be in contact with the water cooling. And then in the next stage here, the top part, that will be the TEC 703. So that will be the 3 ampere or 4 ampere unit, and that will be in contact with the heatsink. And what I will do after that, I will cut out some foam and everything, and I will insulate all the parts. So I will cut out very small tiny pieces, and I will try to make the best insulation, and also I will cover this entirely, because I don't want any heat transfer between the environment and this. So this will be in a sort of a foam capsule, and then I will put a diode-based and a thermocouple-based thermometer inside the fins, and I will fix them with some small piece of foam, so they will be tightly attached to the fins of this heatsink. And we will measure the temperature by two different things, two different thermometers, so we can be sure that we are roughly measuring the correct temperature, because two different temperatures based on two different principles are measuring the value. So that's what will happen. And again, the goal is to reach the lowest possible temperature with this kind of setup. So basically that's all. I will just assemble everything here, and then I will come back. But before that, just about some tools. I strongly suggest you to buy some of these gloves. These are, yeah, you can reuse them because quite strong material, and you should put on these gloves, not because of health, safety or something, but when you apply this thermal grease, this is like so sticky and so annoying to remove it from your hands that it's just better to work with gloves. And also it's very smart to have some kind of cloth and a Q-tip just to get rid of the excess thermal grease that is coming out from between the layers and so on. But this is just some bro tip or something like that to make the work environment a bit more cleaner and it's less messed up. So once again, this will look like something like this, and then I will use this is just from the old experiment, but I will use this kind of foam and cut out different small pieces very carefully, and I will precisely try to attach to the heatsink and everything, as you can see here. And we will measure the temperatures, and I will use water cooling in this particular experiment, and I will probably replace the water here with more colder water. So I have a bottle of water in my fridge. I put it there last night, so that will be used in this system. So at least in the beginning, when we start the experiment, the cold side temperature of the bottom unit will be much colder than we expect, and then we will see that how the numbers will show up later when the temperature starts to change inside the system. And of course we will see the temperature change by this unit, and maybe I will also put in some thermometers in this, because in the whole of the tank there is enough space to put something inside. So yeah, let me just prepare everything, and when the system is ready I will come back and show you the rest. So I assembled this part, and now it's everything aligned almost perfectly. So I can see that everything overlaps very nicely here. Sorry, the tubes are too rigid, so I don't want to move this, because if I start to twist it, then it might happen that this gets misaligned. So I hope you can see it. still, yeah, you should see it in the corner at least. So what I have here is in the bottom I have the 15 ampere unit, and on the top I have the 3 ampere unit, and then I have the heatsink. So the next step will be to cut the foam and use some cloths and stuff to entirely insulate everything, but mainly the top part. So what I will do now, I will try to cut these things properly and create a box which will insulate the heatsink, and then I will install the thermometers, and then I will come back to you and do the experiment. So we have everything connected and running, so let's go through the different thermometers. So I have the channel 1 here at the same spot where I have the K-type thermocouple, which is connected to this thermometer. So they are here in the heatsink, and in practice, or in principle, the thermometer, which is measuring here the 24 degrees, is squeezing the K-type thermocouples against the heatsink. So they are really at the same, let's say, system. But they are a bit different, so 24 degrees versus 28.3. So of course they will not measure the same temperature, but we can see that we have data from 2 different sources. And then we have the channel 2, which we know from my previous video where I was building this, that the resistance of that device is a bit higher, so there is a different voltage drop when the temperature is measured. But this 28 degrees will be measuring the other side of the fan here, so that will be measuring the outlet temperature of the radiator. And then we have the number 3 unit, which is inside this tank, so it is measuring the water temperature, and that is like 24.4 now. And also the water temperature measured here, which is 27 degrees. So again, 2 different types of thermometers and 2 different types of numbers. And then we have the number 4, which should be this cable here. I just touch it and then the temperature goes up. So this is this cable. I will put it here, you can see the end of it, and this is just the ambient temperature. And then I have the 2 power supplies. I haven't touched them, so they are not running yet. I have to adjust them and I have to start them up, but they are here in the corner, so they are somewhere there. You can see some of the cables. So first of all, I will start the 15 ampere unit, and I will go up to 15 ampere and 15 volts. And then when I see that the temperature starts to change on the heatsink, I will turn on the other cooler, which is the 4 ampere unit, and that is on the top, so that is in direct contact with the heatsink, and that will be running at 4 amperes and 16.5 volts. So I will write these numbers on the video, of course, but I just tell them so you know. So I will use this clamp meter to measure the current running in the wires, and then we will see everything. But now, since everything is connected and wired up and the water is running, I will start the experiment. So now I start up the power supply. And the power supply is on, so let's go up to 15 watts, so 15 amps of course. So now I'm at 13 amps. So this should be something like 15 amps. So you can see that the water temperature is going up, and we see that the heatsink started to cool down. So I measure the current. It's a bit difficult to adjust the current, it's very sensitive here. So now we are at almost 15 amps. Okay, now. So we are at 15 amps. And you see that the temperature dropped now here, 14 degrees on both sides. So I just wait until I generate the temperature difference, the DT, that I want to reach with this thing. And then I will turn on the other device as well. But let's go down to 0 degrees here, and then we can continue the experiment. But you can see now here that 34.8 degrees, and also what I measure here, I think you can see the end of the thermometer, that is 32. And also you can see that the radiator is giving out that 32 degrees. So that's quite neat that it can push through the heat. And I can feel that the warm air is really coming out from the radiator, so that's pretty crazy that we have some heat here, generated heat. And meanwhile my camera is losing some power, so the battery is getting low, so I will get some power source here and try to connect to it. So now we have some power on the camera as well, and you can see that 37 degrees here. So just imagine how hot can be the hot side now. So it's really, I think it's 50 degrees easily. I cannot measure it, of course, properly, but we can like assume that it's higher than the water temperature. But you can see that the thermometer is already at almost 0 degrees, and the K-type thermocouple is also approaching 0 degrees. And also I can hear that the power supply is sometimes turning on, so that means that there is a lot of consumption going on. But let's say that we are satisfied with this temperature, so we have to turn on the second stage. So I turned on the power supply of this thing, and then I adjust the current, so I make it possible to reach 4 amperes, and I crank up the voltage to whatever, and then now I turn on the power supply now. Look at these numbers, they are just going down like crazy. And the heat is started to develop in the room, I can feel it so much. So it's getting hot in here. But you can see that the water temperature is also going up as we put out more heat, because now, if you remember, now we are generating roughly 80 something watts on the top side, and that is added to the heat which is traveling through the water basically. So we heat up the water, and then that goes into the water tank, and then it goes into the pump, into the radiator here, and then it gets dissipated. But you can see now the water temperature is 40 degrees, so just imagine how high the hot side temperature could be. I really hope I don't destroy my device. But now what I can see, and I will take a picture of this, I can see the voltage values on the power supplies. So I just take a picture so I can remember it, and then we can go back to the charts and have some conclusions. But what I see here is that on the small power supply we are at 18 volts and 3.8 amperes, and let's see what is that in reality. Yeah, 3.9 3.88 on the power supply and 3.9 by the clamp meter here, so that's quite close. And then the other power supply, the big one, is showing us 14.57 amperes and 17.5 watts. So let's see what is the current in reality. 15 amps, perfectly 15 amps. So that's fine. But as you can see, the voltage values are not the same as we assumed. So that means that the temperatures are also not the same, and that's probably happening on the hot side. So maybe it's like too warm on the hot side, and that's like a big problem. But you can see that now we are at minus 17 degrees, so we are going down nicely. The water temperature is 42 degrees and also 40.7 in this tank here, so they are very close to each other. I don't know what can be the hot side temperature, but I guess it's warmer than that part there. The ambient temperature is 24 degrees, but I can feel the warm air, so yeah, it's quite warm. Then we also have the outlet temperature of the radiator, and that is 39 degrees Celsius. So that's also something. It's very close to the water temperature. So what I suggest now, I will switch into time-lapse mode. I wait for several minutes and we will see how the temperature develops. And maybe I will have to adjust the current, and we will see where this stops after 5 minutes, and after that stops to move, then we will see if we have to adjust the current or not. So let's switch to time-lapse mode now. So 5 minutes passed, and you see that the temperature did not change too much, and this is actually a temperature that a single device can do. So I assume that the bottom stage is too hot, and that's why we don't get the values in the same way as we would expect them. So what I do now, I decrease the current on the big device, which is in the bottom, and we will see what happens. So now we have 14.6 amperes and 17.76 watts. So I go down to roughly 13 amps. 17.7 watts. So let's decrease the things until we reach 13 amps. So I went down to 13.2 amps, and now you can see that this temperature is dropping down. So that's something that we want. So let's see if these two temperatures, so this temperature and channel number 1, will go further down. But I really expect this temperature to be much lower, at least by 10 degrees. But now it's not even going down below one single device. So I waited a bit, and I also changed another thing, which was the top Peltier's parameters. So now I'm fixed at 3 amperes, and if I measure it, then that's also 2.99, 3 amperes with the clamp meter. I can show it, I think. So this is what we got, and then I measure the other value, which is 13.52, and 13.52 amperes at 15.36 volts, and the small device was 3 amperes and 12.47 volts. So I will do the calculations based on these values, or if I get some other changes, then I will use those, but I have to say these numbers so we remember them. But you can see that we are at minus 33 degrees with both, and now the difference between the two thermometers is basically just 0.2, 0.3 degrees. So we can be sure that the temperature is really what it is shown on the screens. And what we can see that we have the temperature on the outlet, and that's 39.6. That's the hot air coming out from the radiator. And then we have the warm water measured here, 49.1 degrees. Sorry, 41.9 degrees Celsius. And then we have the 39.6, which is this water here, and we have the 25.1, which is this guy here. So that's all. So as you can see, the temperature is moving, but it's moving slowly, so we just have to be a bit patient. But what I suggest is that we wait like 10 minutes, I see what happens here, and if there is anything like consolidation of temperature or something like that, so if it starts to level off and doesn't decrease anymore, I will change the parameters of the power supply again for both Peltier devices, and then we will see what is happening. So let's check back in a few minutes. So after a few minutes we moved down to minus 36 degrees Celsius. That's quite nice, and we can also see that actually the water temperature decreased. So what we can assume from this, that we can actually put more heat into the system. So what I will do, I will increase the current on the top side Peltier unit, so on the 3 amperes. So now we are at 3 amperes, so I go to 3.2 and we see what will happen. So now we are at 3.2 amperes, and I will measure it as well. Uh, 3.15 according to the clamp power meter or multimeter. So we are somewhere between 15 and 20, I would say. So now we have to wait another few minutes and see what happens. And if the temperature doesn't move there, that suggests me that we are not removing enough heat with the bottom heat Peltier element. So then I have to increase the current on that part as well. And well, actually we can do it now because the temperature actually increasing. So we are moving away. So that means that we might want to increase the cooling power on the bottom side. So let's check the current there. Yeah, you see 0.4 degrees. So now we are at 13.5 amps. So I will go up to 14 amps. And now whatever temperature change is happening in the system, the Peltier will be very sensitive for that, because now there is literally 70 degrees difference between the two sides. So you can see that now it's very, very sensitive. And as I can see, the temperature is still increasing, so I might have to increase the or decrease the current on the small unit. So I went down to 3.1. So seems like this is a bad idea. So what I will do to try to recover from this mistake, I will change the current of the big power supply, which supports or supplies the bottom Peltier. So I go down to 12 amperes and see what happens. Okay, this is roughly 12 amps and 13.6 volts. So let me quickly calculate the power. 163 watts of power just from the heat generated by the current passing through it. And then of course we have some sort of cooling performance, which I just don't know because I don't have the charts in front of me, but I will put it on the video and I will add some subtitles to tell you the numbers. And now seems to be okay because now the temperature is decreasing again. So let us see what happens. So now it seems like that this is what my cooling system is capable of. I was trying to play around with the parameters, but I could not reach below this temperature. So it seems like that the hot side is very hot. So of course it's larger than 40 degrees, therefore I cannot reach the calculated numbers, which is around minus 56 degrees, so 19 degrees down more. So what I will do, I will cheat a little bit. So here, this is half a liter of very, very cold water. I don't know the temperature, but we can easily measure it. So let's check the temperature of the water. Now it's the channel 4. Okay, my fridge is quite nice. 7, 6, it should be roughly 4. But yeah, so we can see that it's lower than 6 degrees now. Yeah, it reached. I don't want to wait that much. So now what we do is I have a funnel inside this thing. It's just not visible, it's out of the picture. So I open this valve just a little bit. So when I see that the water is going down slowly, I will slowly replace the water. So now I just adjust the thermometer to put it to the bottom of this thing. And now I open this valve. So I will get this water out into another bottle, and hopefully I don't mess up anything. So now I see that the water level drops, so I have to replace that water. So you have to see this temperature, if it changes or not. Because now what I do, I directly mix the hot water, which is exiting the Peltier unit, before putting it into the radiator. So it's not the best idea, but this is what I can do now with this kind of setup. So I will use the whole jug of water and replace the whole hot side temperature and see what happens. But you can see that we already have a temperature drop. So now at least we reached the 37.5. So I mean, this is like a very clear evidence that our hot side is just hotter than we expected it to be. We still have water, roughly 2 deciliters, so I keep adding it, and then I will close the valve and we'll see where we end up. But you see now we are at 38.2 degrees, so we already improved 1 degrees. So another takeaway message: don't do these experiments on a hot summer day. Now literally it's one of the hottest days of the year, and I think outside it is like 28 degrees roughly, so it's quite hot. So now this is empty, as you can see, and I have to close the valve quickly before I run out of the water. So now I think you can see the water level, but it's at my finger now, and the temperature sensor is just down here in the bottom. So now you can see I think we will reach minus 40 degrees. Actually this guy here is showing minus 40, the other sensor, so I'm pretty sure that this will catch up soon and show the values properly. So I will take a picture of the power supply and everything, and we can see what happens after that. So let me take a picture. All right. So I just took a picture so I know the values of the current and the voltage, but you see now that we reached minus 40 degrees, and I dropped this temperature by a significant amount, as you can see. That was very important, but we crossed this magic number, so we are at minus 40. So I guess I will never reach minus 56 degrees with this kind of setup, because the hot side is just getting too hot, and because of that I cannot remove the heat efficiently, and then I cannot go down to more deeper. And I see that the ice is forming on the heat sinks, but not too much, because now I have an enclosed part here and I try to insulate it very nicely. You will see it on the pictures, and I will also take a picture of this, or try to take a picture of the icicles or dendrites which are growing there, because it's very nice. So the ice is just a little bit on the heat sinks. There is not too many ice particles, or how to call it, crystals, because of course I enclosed this small humidity only, and there is no humidity entering, or not too much humidity entering from the environment. So therefore there is just a very little amount of ice showing up on this heatsink. But now you can see that the temperature started to increase, because the temperature of the cooling water started to increase, and then you see that there is like a critical value where, because of the hot side or cooling water temperature, the cold side temperature also starts to increase. So this is it. So you could see that this is quite a challenging task, especially if you have some warmer summer day when you try to test all of these things. So I think I will stop here, because these devices are eating a lot of power, and I just don't see any benefit of running this for hours, because we will not be able to go down more in temperature. So what is the takeaway message of this? That we have to make sure that the cooling of the hot side is very good and very efficient. If I was running the tap water through this continuously, and that would be like 10 degrees or something like that, then I could go down maybe to minus 45, minus 50 degrees maybe, by fine-tuning the power supply values and so on. But with these circumstances I was only able to go down to minus 40 by cheating a little bit. So that's a bit pity, because I was expecting a bit lower temperatures. So this is what we get, and I hope you learned something from this, especially from the introductory part where I showed you the challenges of the stacking, and you see that it's basically pointless, because now we are not removing too much heat from the top of the top side Peltier, so from the cold side of that. And that means that we cannot really use it for anything, because now we are not doing any, let's say, useful work with it. We are just running it, and we are letting its cold side to cool down to very low temperatures, but it doesn't do anything useful. And as you cool these things down, then of course their efficiency drops as well, so it makes no sense to use them below a certain temperature. And I think maybe minus 20 degrees is the sweet spot, or that area is the sweet spot, because then if you keep them stacked, you can still remove efficient heat. And just to mention some idea about the stacking is that now we are using the same surface area of the Peltier devices, and how we could cheat is that we could use a larger surface area for the bottom device and a smaller surface area for the top device. Therefore the heat coming out from the top device would be smaller, and then it would be easier for the bottom device to keep it cool. And actually, if you look up stacked Peltier units that you can buy on the internet, for example, or in shops where they sell these things, you could see that these stacked devices are they look like a pyramid or something like this. So when you sort of like stack them on top of each other, then the next unit will be always a smaller unit, and by that you basically eliminate you eliminate part of the effect which is coming from the Peltier device, because then you have just half of the, let's say, original size of the Peltier device on the top, and that's like half of the heat load maybe, or I don't know how the heat scales with the size, but if it's linear, then let's say half. So if you cut the device into half, then you just transfer half of the heat, but I don't know precisely. So yeah, you should do your own research on this, but it would make sense to have it that way. So what I want to say that if we could, for example, combine the power of the cooling power of 2 or 4 devices and then put another on top of it, then that would be better. And maybe I will try that, because I have a 80 by 40 millimeters, and also I have a 120 by 40 millimeters water cooling block. So I could use those to create a larger surface area of Peltier devices, but I don't think that it worth the struggle. So I will not go with that, I think. So yeah, I think I stop the video here. So this was quite a long video again, sorry, but there is so many information and ideas to share, and I want you to get most of the numbers and ideas and everything, so you can build your own device and play around with it. And yeah, so I stop here. I hope you enjoyed this video. I think it was quite exciting and quite interesting to see all these small factors which are influencing the different temperatures here and there. So you can influence the temperature, most importantly, with the cooling medium's temperature, which is the water's temperature, and then you can influence the temperature, of course, directly by the current which is running through your devices. So that's very important. And of course the ambient temperature, because that is basically the temperature of the air which is entering the radiator and cooling down the hot or warm water which is running through these pipes. So that's also an important factor. So you have to consider this, and also you have to consider the insulation of this system. So yeah, I hope you learned something. I hope this video was interesting and somewhat useful to you. And please subscribe and leave a comment if you are interested in any of these things, and I'm very happy to discuss the ideas. Let me know if I'm wrong somewhere, so I can improve my knowledge, and I can also develop new ideas based on the improved knowledge. So that's all, and see you in the next video.